Right, the next one we're going to look at is the phase lead and PI control. So this is a little bit more complicated. It's probably about as complicated as it gets. So here's the phase lead here, and here's the PI controller here. Now, in this format, they're a bit tricky to handle. So what we're going to do is convert this one now into the standard form, which is easier to do as a state space equation, which is with the k A minus b of this must be, with the output from this state P, and then the PI controller, there's the proportional, and here's the integral here with this output as the state Z. So we convert from here to here first, and then we can start to develop then the control laws and the state space equations. So looking at our standard phase lead equations now, we've got P dot is minus BP plus K A minus B B minus CX, which is the error. So this is the one we just did a moment ago. There's our standard phase lead expression there. We've also got that Q, which is the output from here, is equal to K times the error plus P. So here's an equation now for Q here. We also know now that the input into the integrator is in fact Q. So we've got Z dot is Ki times Q, but Q is given by this expression here. So it's given by Ki into K B minus Cx plus P. And so the overall control law, which is the signal here now, is going to be given by Kp times Q, but Q, remember, is V minus Cx plus P, so it's going to be Kp times this term here, plus Z. So here's our overall control law now for the phase lead plus PI. Now we can now start to formulate the closed loop state space equation. So we've got the states X, the integrated state, and the phase lead state. So X dot is equal to AX plus BU and nothing else. That's our first line. Z dot is given by this expression here. So it's going to be Ki K minus C times X. That's Ki K C times X plus Ki K times V, Ki K times V, plus Ki times P. That's going to be the Ki times P there. So that's our second line in our state space. The third line, which is our standard phase lead, which is P dot is minus BP plus Ka minus B into the error V minus Cx. So this part here is here, and Ka minus B times minus Cx is K minus Ka minus B times Cx, and finally Ka minus B times V. So it's Ka minus B times V. So this is now this gives us an expression now for the closed loop state space equations. So this one's now got a number of states here, plus an extra state here, plus an extra state here. So it's grown its number of states, and this has grown similarly in complexity. So that means that the control law was given by this expression here, and the stability then we could assess by looking at the stability of the eigenvalues of the closed loop system equations. And so if we've got some complicated arrangement now with PI and phase lead, we can always rewrite that in state space form in this form here, and this would then work for any A matrix. So this is the little simulation that we've set up to check everything's okay. We've got a PI controller, phase lead compensator, and again a little transfer function here. We put in the state space equations here, running it again. We're also working out the closed loop state space equations using these expressions here and putting those into here. And then if we've done it correctly, all three should look the same. So here's our closed loop system, and here now is the MATLAB code that does that. So if I now take this bit here and copy this, this is the same sort of code as we had before. Just go over it quickly. This time is the original A matrix for the state space. Got A is 1, B is 10, K is 12, KP is 4, KI is 30. This time ACL is a 5 by 5 because this is 3 by 3, so 3, 4, 5, 5 by 5. B is going to be a 5 by 1 and C a 1 by 5. So the first part is going to be, I need to compute, is, something's gone wrong here, is, this isn't right, is it? This expression is incorrect. Cut that one out, and let's do a correction, so it should be this one here. Do a copy and a paste. Let's make it a bit smaller. Bring it into here. Here we go. That's a better correction now, isn't it? So the first part should be A minus B KP KC. So that's A minus B. Oh, these are the wrong way around, don't they? This should be, it doesn't matter though because they're scalars. So it should be KP times K. In this particular case, KP and K are scalars, so it doesn't actually matter, but we might as well do it absolutely correctly. And then that sticks that part in there for us. This bit of code here sticks that bit in. Then next part is for 1 to 3, we're getting A5. So that's going to be, this is 3, 4, 5. So A5 is going to be minus K, A minus B times C. So that's doing that part there first. That line there is doing that first. Then we've got a 4, which is this one here. So that's going to be minus KI, KC. That's the KI, KC there. Then we've got the B to fit in. That's going to be N4 now. So this is in the 4th column, because this is a 3 by 3. It's the 4th column. That's fitting the B in there. Then this part here is fitting in the, well, it could be B times KP or BKP. Technically, it should be, if we keep the labels in the right order, it's BKP, so that's the BKP. So this line here is putting in the 5th part in that, putting that one in there. Then the 5, 5 is putting as minus B, and the 5, 4 as KI. And then, so that's quite a bit of this sorted out. We needed to get this bit sorted out now. So we got 1 for 3. The closed loop B is going to be B times KP times K. So we'll just make a slow. They don't actually change these because they're scalars, but we might as well make it perfect. So that's going to be BKPP, and that's filling in that slot there. Then we've got KIK. It's just one parameter going in there, and then we've got the 5th one is K A minus B. So that one there is that one there. And finally, we just fill the C up with the first 3, and then the rest is 0. And so this now has formed the closed loop state space equations for us. And I've converted this into state space equations, or into a transfer function even, using this little bit of code here. So it says this is this closed loop state space equations, converts into a transfer function and puts its poles zeros. So that's the closed loop transfer function now, as poles and zeros. And what I also did was I multiplied this by this by this by putting them in as transfer functions, did a feedback around it as well, and then came up with the same answer. And you can see that this term here is identical to this one here, indicating that all the calculations have been done correctly. So that's another way of getting at our closed loop thing. If we take this code here now and copy this, do a copy, and then we can go down to MATLAB and open up a new script. So you've got a new script here, paste this in, and then run that code. It's going to call it on the other thing, and then we can get here ACL. So this time ACL is going to be a 5 by 5. So there's the 5 by 5 ACL. I can get BCL. There's my 5 by 1 BCL, and CCL. There's my CCL there. And so that's a quick check that I've done those correctly. Can then go into the simulation now, which is here's my phase lead, there's my PI, and here's my closed loop state space equations. So if I now run this one and have a look here, again we see all three outputs looking exactly the same and indicating that we've worked out the closed loop state space equations correctly. So there's another example now of, it's about as complicated as it gets. This is a PI controller with phase lead. So we start off in this format here, and then we convert it into this format here because it makes it easier to do the state space analysis. This means adding two extra states to the state space. That's Z and P, which gives us the following closed loop state space equations, which we can then compute in MATLAB and then do a simulation if we need to in Simulink. So let's have a look at what we've learned from this. So we should have learned how to define a mathematical equation called the control law for a linear time invariant system, how to include the control law into the state space representations. That can be by, if it's proportional control as it is, if it's integral control adding in a state, phase lead adding in a state, if it's PI and phase lead adding in two states. So we've looked at how to add in integral states and phase lead states into the open loop models. And then we've seen how to form closed loop state space equations, assess the stabilities using eigenvalues. And I think equally as important is you can also use your MATLAB Simulink to generate the closed loop state space equations and compare those with your block diagram of transfer function forms. This gives you a guarantee when you do this that the closed loop, if this is the closed loop system in block diagram, and this is your closed loop system in state space, if the outputs from the two are the same, you know you've made no errors. So you should also have learned maybe how to double check that your state space equations are in fact correct. So as a little exercise for you, if we take the system that we had, using hand calculations, form these closed loop state space equations. You've got the answers in front of you, but you could actually have a go at forming the closed loop state space equations, and you could then obviously check it against your code, but have a go at doing this, taking this, simplifying it into the alternative forms, working out all the state space equations by hand, and then comparing it with the MATLAB solutions. And if you do it correctly, you'll be the same as MATLAB. If you do it incorrectly, then you'll know because MATLAB will tell you that you've done it wrong. So hope you enjoyed that. That's closed loop state space equations. And knowing that, you can do just about every closed loop state space equation under the sun. Right, so this part 2 now, on control laws, is on phase lead or phase lag compensators. Now these look like an S plus A over an S plus B with a gain on K. And if B is bigger than A, it's a phase lead, whereas if A is bigger than B, it's a phase lag. Now, as this stands, it's a bit tricky to convert into state space equations, but we can play a little trick here. So this whole part here we can write as K, S plus A or S plus B, which we can rewrite as K plus K A minus B over S plus B. So this is a very handy format now, because it means we can rewrite this little part of our block diagram as the following diagram. It's K, which is this one here, plus K into A minus B over S minus B. So if we add these two together, this block is the same as this one. And we can now define the output from this block here as a state P to get a state space equation. And then from this overall block diagram, we can generate our control law, which is the signal here. And this is the control law, the U into the state space equations. So this is a nice little approach now. So let's have a look at how we could do this. So looking at just at the little lagged unit here with the pole at minus B, the output from this is P. The input, remember, is the error, which is V minus Y. So the input is V minus Y and the output is P. And this box now has got K, A minus B over S plus B in it. So we know that P is this times this, which gives us this little equation here. Then we can move the S plus B up here to get P, S plus B, K, A minus B times B minus Y. Now P times S is P dot. P times B moved on to this side is minus BP. And then we've got K, A minus B times V, and K, A minus V times the CX. And the control law now, U, will be K times the error plus P. So here's our control law. So here's an equation now. It's an extra state, which we're going to have to add in to our control law. And here is our control law. So between these two equations now, we can move forward to look at the closed loop state space equations. So here we have now x dot is x plus bu, that's our standard state space equations. Here's now our phase lead compensator with the u here. So we've got p dot is minus bp, k a minus b, v minus cx, and u is k e plus p. So here's a x dot is a times x plus b times u, and then nothing else. That's the first line. The second line, p dot now, is going to be k a minus b times minus cx. That's going to be a minus k a minus b times c times the x minus a bp. So that's that times that. No u's, and a k a minus b times v. That's the k a minus b times v. That's that term there. So that then gives us, we now put u equal to k v minus cx plus p. So we're going to get a b times kv, so that's going to give us the bkv. We're going to get a b times k times c times x. That's going to give us a minus b times k times c times x. And finally, we're going to get a minus b times p. That's b times p there. So this now forms our closed loop state space equations. And having formed our closed loop state space equations now here, we know that stability is given by the eigenvalues of this matrix here. So this is a new matrix now for a unit with a phase lead in. We could have a look at the performance of this in, again, looking at the three separate systems. We've got the standard feedback control system. We've got the feedback control system with some state space equations in here, and we've got a closed loop state space equations here. And we could form these now with the following bit of MATLAB code. So the A, this first part now just sets up the transfer function here for us, and in companion form. So that sets up the companion form state space equations. This time, this is 3 plus 1 is 4, so ACL is a 4 by 4, BCL 4 by 1, C 1 by 4. And the first part of A is A minus BKC, so that's going to be A1, that is A minus BKC. And then this goes into the first 3 by 3 elements. That's what that does there. The next bit of code has to put in this term here. So this goes on the fourth line. We need to put 3 numbers in. So it's it's the fourth line where n can go from 1 to 3, and it's minus k1 a minus b minus k1 or k a minus b times the c, and it's c1n because it's 1 by n, and n goes 1, 2, 3 to fill up the 3 boxes there. Then we know that an4, that's the fourth column now, is the same as b. So we put 1, 2, 3 values of b in there. And then we know that a44, that's this element here, is just minus b. So that's filled in this for us. We know also that the new b, which is called BCL, is equal to b times k. That's for the first 3 elements there. And the fourth element, that's 4, 1, is k a minus b. And then the c is the same as the c, but with the last element to 0, and DCL is 0. Then if we then take this system here, form it as a state space representation in MATLAB, convert it into a transfer function, and do a ZPK, we'll then get the closed loop transfer function for this system. And that's how we could look at phase lead. Just to have a look at this work, if we were to take this code here, so I could just go into there and copy it, do a copy, and then go into MATLAB and do a paste here and run the code. I'll call it phase lead 1, and then we can look at ACL. There's the closed loop. This is that's the a minus b k3. That's the a minus b times k times c. There's the b. And there's the b matrix, which is 0, 0, 1, and then there's the minus 10 for the minus b there. If we do BCL, there's the BCL there, and if we do CCL, we get the C matrix with a 0 in the end. And now if we go on to the MATLAB simulation, I put a gain of 120 in here just for I fancied it, and we run this now, we can look at the output here. So that's the output expecting, and if we look at all 3 simultaneously, we get all the same, clearly indicating now that the closed loop system here is the same as the closed loop system here, it's the same as this one. So this is now given us, if we want to get back to the closed loop transfer function, if we look at sys12 here, this is what getting the forming the closed loop state space equations, and this will do it in pole 0 form. So if we just do ZPK sys12, ZPK sys12, then here is now the closed loop transfer function for that system, which we've just obtained. That's quite good. So that's an example now of doing phase lead control, and these are the underlying state space equations representing phase lead control. Also works for phase lag as well. Okay, so here's an example now of a system with a phase lead and PI controller. And this is the block diagram now of our system. So here's our phase lead, and I've chosen K as 4, A as 4, and B as 8. Just going to check that. No, A as 2 actually. A mistake there. A is 2. Just check my notes here before we get going. Yeah. Then we've got a proportional controller here of 10 and an integral control of 2. And I've got a system here, s squared plus 3s plus 2, s to the 4, 25s cubed, 218s squared, 776s plus 960. So it's a 4-quarter system. Now the first thing we need to do is to simplify this back now into the form that's going to suit our state space representation. And so the first thing to do is split this phase lead into a K and then an A minus B over S plus B. So this is this alternative form of this. I'm going to put the numbers in now. So K is 4, A minus B, A is 2 and B is 8, so A minus B is minus 6 and B obviously is 8. So there's my, I've just got minus 6 in there. There's my phase lead unit now in the correct format with P as the output from this little first order lag here. Next one, we're going to rewrite this as, if we cancelled out the S's, we get Kp, and then we get Ki over S. So we do this Kp, which is 10, and Ki over S, and this is 2 here. And then I'm going to call this signal here Q, and call that signal U, and this is the one associated with the control law. Inside here now, I'm replacing this with some state space equations, and I'm going to do this in companion form, and this is going to go in to my big state space equation into this little box here. So this is my ABC. So the A goes in there, the B goes in there, and now I'm just drawing the C there so you can see what it's like. And I'm going to get a companion form for this. So companion form is going to be 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Can have put 0, 0, 0, 1 in there. And then these numbers here now are these numbers here in reverse order with negative signs. So that's going to be minus 960, minus 776, minus 218, and minus 25. And the C matrix is going to be 2, these numbers here in reverse order, 2, 3, 1, 2, 3, 1, and a 0, because there's no S cubes. So there's my starting off position now. I've added in 2 more states into this, one to represent Z and one to represent P. And the first thing we need to look at now is this box here. And if we look at this one, we've got 6 fours are 24, minus 24, so that's the minus 24 over S plus 8. And the signal coming in now here is V minus Cx. It's V minus Y. So that's V minus Cx. So it's going to be minus 2x1 minus 3x2 minus an x3. So that's my V minus Cx, and that's going into this box to give me the P. So I can then say that this is this times this. So I get that P is equal to, so I'm going to get 24, so I get minus 24V, and then I'm going to get a minus times minus a plus, it's going to be 28 48, sorry, 2 times 24 will be 48, 48x1 plus 72x2 and 24x3 minus 24v, so that's going in that way, and that's going to be all multiplied over the S plus 8. So we've got this is this times this, so this times this, those terms there, the S plus 8 remains there. Then we're going to move the S plus 8 up here, so this is going to become S plus 8 times that. Then S times P is P dot, so get P dot equals, then the 8P on this side will become minus 8P, so I get 48x1 plus 72x2 24x3 minus 8p minus 24v. And here's my p dot equation now. So this is going to go in on this line here. So p dot is 48x1, 72x2, 24x3 minus 8p and minus 24v's. So there's that bit nicely sorted out. I next need an equation for Q here. So Q will be given by 4 times V minus Cx. That's going to be 4 into V. Now Cx will be minus 2x1 minus 3x2 minus x3 plus P. So there's my expression now for Q. Q is going to be 4 times this plus P. And so I now know that the expression now going into my Z, so I've got Z is this times Q, so it's going to be 2Q. So I've got Z dot, if you like, will be given, or I can even say that Z is 1 over S, so Z is 1 over S times 2Q. So that's going to give me 2 times this. So it's going to give me 2 4s 8V minus 2 4s 8 minus 16x1. And I've got 3 4s 12 times 2 is 24 minus 24x2. And I got a 4 minus 8x3 plus P is my expression for Z. If I move the S now up here, then this becomes Z dot. So Z dot now is given by this expression. So it's going to be 8V. This is going to go in obviously on that line. So Z dot is 8V minus 16x1 minus 24x2 minus 8x3 plus P. And here now are my state space equations now, almost coming on quite nicely. Next thing we've got to do now is work out an expression for U. So I need a U expression next, and then I can stick the U into here and feed that in on this line here. That'll be my next job. So let's have a quick go at that next. I made one small mistake here, haven't I? That Z is 2Q, so Z is 2Q, so it's going to be 2P, won't it? If I made a mistake here. That's why I slowed down a bit, so it's actually been a 2 there. 2P. Because it's this is 2 times Q, so Z dot is Q, which is 2P. 2Q, so 2 Q's give me 2P. So our next little task now is to get the control law expression. So if we can just quickly work this out. So now after an equation now for U. So let's go at what U is. So U is going to be 10Q, so it's going to be 10 times this, plus Z. So I'm going to take 10 times this now to get my 10Q. So 10 4 is going to be 40V. And then 2 4s are 8 times 10, so minus 80 x1. 12 times 10 would be minus 120 x2. 4 times x3 times 10 would be minus 40 x3. Remember it's 10Q, isn't it? So it's going to be 10P plus the Z. So this now is my control law, which is the equation describing U. So we put this U now into here. And notice it feeds in on this line here, fortunately, because it's in companion form, through a 1. So what will happen now is this column will disappear, and we will put these terms now in on this line. So we'll get an extra minus 80 there, an extra minus 120 there, an extra minus 40 there. We'll get a 1Z, which means we'll get a 1 in there, and we'll get a 10P. And what will happen then is this will then disappear, and these now are our closed loop state space equations. And if we have a look at these, we can do a quick little check on these. We know now this part here is given by A minus B KP KC, which is looking correct. This part here should look like B, which is 0.001. This one here should look like 10 or KP times B. So KP, remember, is 10. So 10 times this is looking like almost 10. This number here should be KI, which is 2. This number here should be minus P. So minus B, sorry. So B was 8, that's minus 8. This part here, there'll be noughts in there. And this part here will be Ki times K, Ki times K, which is 8 times this. So 2 8s are 16, so that's with a minus sign in, so they look also correct. And the final bit to check is these numbers here, which are given by minus K into A minus B times C. So K was 4, A minus B was minus 6, so 6 4s are 24, 24 times 2, 48, times 3, 74, times 1, 24. So this then looks very much correct. I'm able to check it out against our known sort of solution to this. And so we have to add those numbers up to give us the final numbers in there. But then this now represents the closed loop state space equations of this system here. So that's a little example now of a derivation of the closed loop state space equations for a 6th order system, and how all the various components fit into it, and how we work out eventually to get the control law to form the closed loop state space equations. And bear in mind also, when you do these, you've got to simplify your phase lead into this one, your PI into this one, and then put this ideally into companion form, because it gives you a nice little B for doing the calculations on. Okay, so hope you enjoyed that, and that's phase lead and PI control in state space.